Class 9th, CBSE based. Chapter 2, Matter Around Us, Is It Pure? Introduction to Pure Substances and Mixtures. In everyday language, pure means something with no mixing. But in scientific terms, most things we see are mixtures of several substances, making them not purely single substances. For example, milk contains water, fat, and other substances, so it is not pure in the scientific sense. What is a pure substance? A pure substance is made up of only one type of element or compound. It has uniform chemical properties throughout. Example, distilled water is a pure substance because it contains only HO molecules. Elements. Definition: an element is a pure substance that cannot be broken down into simpler substances by any chemical or physical means. It is made up of only one type of atom. Characteristics of elements. Simplest form of matter, elements are the building blocks of all substances. Cannot be chemically separated, elements cannot be split into simpler substances by chemical reactions. Represented by symbols, each element is represented by a unique symbol, e.g., H for hydrogen, O for oxygen, Na for sodium. Fixed properties, elements have consistent properties, such as boiling point, melting point, and density. Examples of elements. Oxygen, or the air we breathe contains oxygen, but pure oxygen gas, used in medical treatments, is a pure substance. Gold, our pure gold, as found in 24-karat jewelry, contains only gold atoms. Iron, Fe iron used in making tools and construction, when unalloyed, is a pure substance. Carbon, See diamonds are made of pure carbon atoms arranged in a crystalline structure. Types of elements. Metals, elements that are shiny, malleable, ductile, and good conductors of electricity and heat, e.g., iron, gold, copper. Non-metals, elements that are brittle, non-conductors, and often gases at room temperature, e.g., oxygen, nitrogen, carbon. Metalloids, elements that have properties of both metals and non-metals, e.g., silicon, arsenic. Compounds. Definition: a compound is a pure substance made up of two or more different elements that are chemically combined in a fixed ratio. Characteristics of compounds. Chemically bonded, the atoms in a compound are bonded together through chemical bonds, ionic or covalent. Can be chemically separated, unlike elements. Compounds can be broken down into their component elements through chemical reactions, e.g., electrolysis of water. Different properties. A compound has properties different from the elements that make it up. For example, sodium, a reactive metal, and chlorine, a toxic gas, combine to form table salt, NaCl, which is safe to eat. Fixed ratio, the elements in a compound are always in a specific ratio by mass. For example, water, HO, always has 2 hydrogen atoms for every 1 oxygen atom. Examples of compounds. Water, HO pure distilled water contains only water molecules with no impurities. Sodium chloride, NaCl pure table salt is composed only of sodium and chlorine atoms in a fixed ratio. Carbon dioxide, CO. This gas, exhaled during respiration, is a pure compound of carbon and oxygen. Glucose, CHO, a simple sugar used by the body for energy, is a pure chemical compound. Characteristic: element, compound. Definition: substance made of one type of atom. Substance made of two or more elements chemically combined. Separation: cannot be broken down into simpler substances. Can be broken down into elements via chemical reactions. Chemical composition: contains only one type of atom. Contains two or more types of atoms. Properties: retains its own properties. Has different properties from its component elements. Examples: oxygen, O, gold, Au, iron, Fe. Water, HO, carbon dioxide, CO, salt, NaCl. What is a mixture? Impure substances. Mixture contains two or more substances, elements or compounds, mixed together in any proportion. These substances can be separated using physical methods. Example: air is a mixture of oxygen, nitrogen, carbon dioxide, and other gases. Types of mixtures: homogeneous mixture, true solutions. Has no visible boundaries between the components. The composition is uniform throughout the mixture. Examples: sugar in water. When sugar is completely dissolved in water, the sugar particles distribute evenly, creating a clear solution. A mixture of gases like nitrogen, oxygen, carbon dioxide, and others that are uniformly mixed to form air. Salt in water, like sugar, when salt dissolves in water, it forms a uniform solution with no visible boundaries. Vinegar, a mixture of acetic acid and water that appears uniform throughout. Heterogeneous mixture has visible boundaries of separation between the components. The composition is not uniform. Example: a mixture of sugar and sand is heterogeneous because the components do not blend evenly. Comparison of homogeneous and heterogeneous mixtures. Property: homogeneous mixture, heterogeneous mixture. Composition: uniform throughout. Non-uniform, different parts have different compositions. Phases: single phase. May contain two or more distinct phases. Separation: cannot easily separate components by physical means. Components can often be separated physically. Examples: sugar in water, salt in water, air. Oil and water, salad, sand in water. Comparison between compounds and mixtures. Sin. Compounds. Mixtures. 1. Compounds are pure substances. Mixtures are impure substances. 2. Compounds are made up of two or more elements combined chemically. Mixtures are made up of two or more substances mixed physically. 3. The components of a compound are present in a fixed ratio. The components of a mixture are present in different ratios. 4. Compounds have the same properties throughout the compound. Mixtures do not have the same properties throughout the mixture. 5. New substance is formed. No new substance is formed. 6. The components of a compound can be separated only by chemical methods. The components of a mixture can be separated by physical methods. Solutions, a special type of mixture. Solution is a type of homogeneous mixture where two or more substances combine in such a way that the composition is uniform throughout the mixture. Unlike heterogeneous mixtures, in solutions, the particles are so well mixed that they cannot be seen or easily separated by simple physical methods. Components of a solution. Solvent. The solvent is the component of the solution that dissolves the solute. It is usually present in a greater amount and acts as the medium in which the solute is dissolved. Example, in salt water, water is the solvent because it dissolves the salt. Solute. The solute is the substance that is dissolved in the solvent. It is usually present in a smaller amount compared to the solvent. Example, in salt water, salt is the solute because it is dissolved in the water. Explanation with example. Example 1, saltwater solution. When salt, solute, is added to water, solvent, it dissolves completely, forming a uniform solution. Once dissolved, the salt particles are not visible, and the mixture looks the same throughout. This makes salt water a homogeneous mixture, as the salt is evenly distributed in the water. Components. Solvent, water. Solute, salt. Example 2, sugar in water. If you stir sugar into a glass of water, the sugar dissolves and forms a solution. The sugar molecules disperse uniformly throughout the water, creating a homogeneous solution where the sugar cannot be seen, even under a microscope. Components. Solvent, water. Solute, sugar. Suspensions. Definition. Suspension is a type of heterogeneous mixture in which solid particles are dispersed in a liquid or gas but are large enough to be seen and can settle out over time. Characteristics. Particle size. The particles in a suspension are relatively large, typically greater than 1000 nanometers, 1 micrometer. Because of their size, they can often be seen with the naked eye. Settling. The particles in a suspension will eventually settle out if left undisturbed due to gravity. This can be observed when, for example, a mixture of sand and water is left to stand, and the sand settles at the bottom. Separation. Suspensions can be separated by filtration or sedimentation. Appearance. Suspensions are often opaque because the large particles scatter light. Examples: mud, soil particles suspended in water. Orange juice with pulp, the pulp particles are suspended in the juice. Paint, pigment particles suspended in a liquid base. Colloids. Definition. Colloid is a type of heterogeneous mixture where the particle size is intermediate between those in a solution and those in a suspension. Colloidal particles range from 1 nanometer to 1000 nanometers in size. They remain dispersed in the medium and do not settle out. Characteristics. Particle size. Colloidal particles are small enough to be invisible to the naked eye but large enough to scatter light. This scattering of light is known as the Tyndall effect. Stability. Colloidal particles remain dispersed throughout the medium and do not settle out over time. They are stable due to the electrostatic repulsion between particles. Separation. Colloids cannot be separated by simple filtration but can be separated by methods such as ultrafiltration or centrifugation. Appearance. Colloids often appear cloudy or opaque due to the scattering of light by the particles. Examples: milk, fat globules are dispersed in water. Fog, tiny water droplets are dispersed in air. Gelatin, gelatin particles are dispersed in water, forming a gel-like consistency. Whipped cream, air bubbles are dispersed in a liquid cream. Property. Suspensions. Colloids. Particle size. Larger than 1000 nanometers. Between 1 nanometer and 1000 nanometers. Visibility. Particles are visible. Particles are not visible. Settling. Particles settle out over time. Particles do not settle. Separation. Can be separated by filtration or sedimentation. Cannot be separated by simple filtration. Tyndall effect. Does not show Tyndall effect. Shows Tyndall effect. Appearance. Often opaque. Cloudy or translucent. Methods of separation of mixtures. Different techniques can separate components in a mixture, based on their physical properties. 1. Evaporation. Principle: one component has a lower boiling point and evaporates, leaving the other behind. Example: in a mixture of water and dye, water evaporates, leaving the dye behind. 2. Centrifugation. Principle: denser particles move to the bottom when the mixture is spun rapidly, and lighter particles stay on top. Example: cream can be separated from milk using this method. 3. Differential extraction. Principle: two immiscible liquids, that do not mix, can be separated using a separating funnel. Example, water and oil can be separated by allowing water to drain out first. For sublimation principle, one component sublimates, changes directly from solid to gas, and leaves the other behind. Example, a mixture of ammonium chloride and salt can be separated by heating, as ammonium chloride sublimates but salt does not. 5. Chromatography principle, different components of a mixture move at different speeds on an absorbent surface, separating them. Example, colors from a dye can be separated using chromatography paper. 6. Distillation principle, a mixture of liquids can be separated based on their different boiling points. Example, a mixture of acetone and water can be separated by heating the mixture, as acetone boils at a lower temperature than water. 7. Crystallization principle, impurities are removed by dissolving a substance in a solvent and then allowing crystals to form as the solution cools. Example, pure copper sulfate crystals can be separated from impurities by crystallization. Physical versus chemical changes. Understanding the difference between physical and chemical changes is crucial in science. Physical changes. These changes are usually reversible and do not form new substances. Example, melting ice is a physical change because it can be reversed by freezing the water again. Chemical changes. These changes form new substances and are not easily reversible. Example, burning wood is a chemical change because it produces ash, carbon dioxide, and heat. Comparison between physical changes and chemical changes. Aspect. Physical changes. Chemical changes. Definition. Changes that affect one or more physical properties of a substance without altering its chemical composition. Changes that result in the formation of new substances with different chemical properties. Nature of change. Reversible or partially reversible, the original substance remains the same. Irreversible or not easily reversible, new substances with different properties are formed. Examples: melting of ice, boiling of water, dissolving sugar in water, tearing paper. Burning wood, rusting of iron, cooking an egg, fermenting wine. New substances formed. No new substances are formed, the chemical composition remains unchanged. New substances are formed with different chemical compositions. Energy changes. Energy changes are typically associated with physical changes but do not involve chemical reactions. Energy changes often involve heat, light, or electricity, indicating a chemical reaction. Molecular structure. The molecular structure of the substance remains the same. The molecular structure of the substances is changed, resulting in different chemical compositions. Reversibility. Many physical changes are reversible, e.g., freezing and melting. Chemical changes are often irreversible, e.g., burning paper cannot be reversed. Observable indicators. Changes in state, shape, size, or appearance, e.g., phase changes, dissolution. Formation of gas, change in color, formation of a precipitate, release or absorption of heat or light. Examples of changes. Melting ice, ice changes from solid to liquid but remains water. Burning paper, paper turns into ash and gases, with a new substance formed. Dissolving sugar, sugar dissolves in water but remains sugar in solution. Rusting iron, iron reacts with oxygen to form iron oxide, rust, a new substance. Chopping wood, the physical size of wood changes but the chemical composition remains unchanged. Cooking an egg, proteins in the egg undergo a chemical change to form a different structure.